Okay, so let's talk about titration curves. Apparently, these are giving you guys a little trouble. So when you do a titration curve, you're going to have on your x-axis the volume of the titrant or the substance that you don't know the molarity of and wish to find out. On the y-axis, you will have pH. You want to create a smooth, continuous curve, and you're going to plot the data points on that graph and then make your smooth curve from it. So what kinds of questions could be asked? Well, you could be asked, is the titrant an acid or base? Is the analyte, which is in the burette of your titration, is it an acid or a base? One has to be in one place, the other has to be in the other. So if I wanted to know if the titrant was an acid or base, I would look at the initial pH. And if that pH was below 7, I have an acid in my flask. If that pH is above 7, then I have a base in my flask, and the other one must be in the other place. The volume added at the end point. So now you're looking for the point that has the greatest change in slope or is almost vertical, and that will tell you the volume of the titrant that you've added, or amount of analyte you've added. It'll tell you how much you've used from the burette. The pH at the end point, you're going to take that part that's most vertical and find the midpoint of that, go over to the y-axis, and that'll tell you the pH at the end point. If you know the end point or equivalence point, then you know what the half equivalence point is. Once you know the half equivalence point, so let's say the equivalence point was at 20 milliliters. Half of 20 is 10. So the half equivalence point would be at 10 milliliters. And if you go up from 10 milliliters on your x-axis to your curve and then come over to the pH on the y-axis, that'll tell you the pKa if it's an acid that you're analyzing, or the pKb if it's a base, if you started with a high pH. It will also tell you if the stoichiometry of the reaction is 1:1. If it is, you'll only see one vertical section on your curve. If you see two vertical sections, then it is a 2:1 acid base, like H2SO4 with sodium hydroxide. pH at the volume added, including 0 milliliters, you need to be able to plot points. Even though you haven't added any of your titrant yet, you need to be able to plot the pH, and that'll tell you something about if it's a strong acid or weak acid. You can calculate the molarity to begin with. Sketching a titration curve is pretty straightforward. Just kind of slowly move through the dots. You should be able to identify where buffering occurs. That's where you would have your, let's say we've got an acid in our solution in the flask. That would be where we have both the acid and its conjugate base. The Henderson-Hasselbalch equation is useful in finding the, if you're at the half equivalence point, it'll get you the pKa of your acid relatively quickly. So here's an example of a pH curve. This one, since I'm looking at this graph, can tell in my flask I had an acid because my pH is below 7. I also know that that acid is a strong acid because the pH from 0 to about, 22 milliliters is fairly flat. So it's not changing much in pH. I'm not seeing a lot of buffering region. Then that goes shooting up between 20, probably right around 25 milliliters. And now the pH is being controlled by my base, which is what I'm adding from my burette. And it is also a strong base because that pH is high enough that it has to be a base that completely disassociates. This one would not have any buffering region because this is a titration with a strong acid with a strong base. And I can tell that from this region being very flat here from 0 to about 25 milliliters. And this region is also very flat, and this is where the base controls the pH. So here's a titration curve where I have, looks like a strong base. I know that because it's very close to 14 in terms of initial pH. I know that that means this is a base is in my flask. And since this is my ending pH, this is also very strong. So this is again a titration curve with a strong acid with a strong base. The strong base is in the flask, the strong acid is in the burette. The equivalence point is here at 10 milliliters. The pH at the equivalence point, if you go from here, which is 12, down to here, which is 2, 12 minus 2 is 10. So I want to go up 5. So 1, 2, 3, 4, 5. Come over, and that pH is 7. So this is a strong acid with a strong base. Strong base is in the flask. This would be an example of a weak acid, and I know it's weak because this kind of, they call it a shoulder region, is kind of broad and smooth curve, looks like a shoulder. The pH is starting above 1 or 2, so the pH is fairly high, means this is a weak acid. My equivalence point is roughly here, which looks like it might be, I don't know, 32-ish. The pH at the equivalence point is up here, probably at about, I don't know, 10.5, 11. This also looks like it's a weak base. I won't be giving you any of these kind of titration curves because they're more difficult to analyze. Here we have some dots on a graph. This looks like fun, right? So here's my first equivalence point, and here's my second equivalence point. My pH is starting below 7, so this is a weak diprotic acid, meaning it has 2 hydrogens that can ionize. It is a weak acid because the pH here starts above 1 or 2, and it is got this shoulder region. This is the area where my first buffer region occurs. This is my half equivalence point because it's halfway to my first equivalence point so this is my first half equivalence point. And so the pKa of that first hydrogen on this is about 4. So that's 1 times 10 to the negative 4th is the Ka for that first hydrogen. So here's my pH at my first equivalence point. It shoulders again, so this means it's a second weak acid. Here's the second equivalence point, D, at about 40 milliliters. Halfway to 40, between these two equivalence points would be here at 30. And so the second half equivalence point is point C, and it is at a pH of 8, so the Ka for that second hydrogen is about 1 times 10 to the negative 8th. You do the inverse log, you can figure it out. And then this is once a pH is being controlled completely by our base. So what you do in this kind of work is you are going to plot along this bottom axis, your x-axis, the amount of titrant, or the amount that's been added from the burette. And on this scale, the y scale, you're going to put your pH numbers. And then you would slowly draw your continuous curve. And you should be able to identify your equivalence point, half equivalence point, etc. So I am going to do another video where I work through a problem, but I wanted to give you a bit of background on it first. Thanks for watching.